Have you ever wondered what the secret ingredient is behind some of AI's biggest, most spectacular achievements? It's not always some revolutionary new algorithm. A lot of the time, it's something way more subtle, something working quietly behind the scenes. This is the story of the unseen dials of AI. Okay, so let's go back to 2016. I'm sure you remember this. DeepMind's AlphaGo did something that people thought was decades away. It beat Lee Sedol, the world champion at Go, one of the most complex games humans have ever invented. It was a massive moment for AI. But the story of how it actually won is, I think, even more fascinating than the win itself. And here's the twist. It turns out there was another program constantly in the background tweaking and adjusting AlphaGo's internal settings, hunting for the absolute perfect configuration to make it play just a little bit better. So one AI's huge public triumph was really made possible by another AI working as its master tuner. This whole process, this secret weapon, is called hyperparameter optimization, and it's one of the most critical, yet unsung, heroes of modern machine learning.
So, what's the big deal with this tuning process? Why is it so important? Well, it turns out that having a powerful algorithm is only half the battle. If you don't get the settings right, that powerful algorithm might as well be completely useless.
Think of it like this. Imagine you have a Formula One car, an absolute beast of a machine, but you don't know how to adjust the suspension or the gear ratios for a specific track. You're going to lose the race, right? Doesn't matter how powerful the engine is. It's exactly the same with AI. The wrong settings can lead to terrible performance, and when these models can take days or even weeks to train, that's just a colossal waste of time, money, and energy.
Now check this out, because this slide shows a really fascinating experiment. Researchers were doing sentiment analysis, and they compared a simple classic model, logistic regression, against a really complex, state-of-the-art convolutional neural network. Now you totally expect the complex network to just blow the simple one out of the water, but look at the results. When they carefully, meticulously tuned the settings for the simple model, its accuracy was almost identical to the fancy, complex one. It's a perfect illustration of how smart tuning can be just as important, if not more so, than having a sophisticated algorithm to begin with.
Okay, so let's get a little more specific about what we're talking about here. These settings are called hyperparameters. They are the high-level configuration choices for a machine learning model. Now, the key thing is, unlike the model's internal parameters, which it learns from looking at the data, hyperparameters are the dials and knobs that you, the human, have to set before the training even begins. We're talking about things like the learning rate, how complex the model should be, what kind of regularization to use. All those dials have to be set just right. So if these settings are so critical, how on earth do we find the right combination? With dozens or maybe even hundreds of these dials to turn, trying out every single possible combination is completely impossible. The numbers just get astronomical fast. So we're going to need a strategy. Probably the best way to wrap your head around this is to imagine a giant invisible landscape, a massive terrain of mountains and valleys stretching out in every direction. Now, each point in this landscape represents one unique combination of all our hyperparameter settings. And the altitude of that point, how high or low it is, represents how well the model performs, or actually how high its error is. So our goal is simple. We have to find the absolute lowest valley in this entire landscape. The catch? We can't see the map. We have to find the best settings by strategically exploring. Now, in technical terms, this invisible landscape is called the response function. And every single time we try a new set of hyperparameters, we have to train the entire model from scratch and test it to get just one number back, its error. Each of those tests is like sending a probe to a single spot on our invisible map to measure the altitude. And since each one of these probes can be incredibly expensive, taking hours or days, we want to find that lowest point using as few probes as we possibly can. Okay, so how do we search? Well, two of the simplest strategies are grid search and random search. Grid search feels really intuitive, right? You just create a neat grid of values for each dial, and you test every single intersection. It's systematic, but it's also deeply, deeply flawed. The more dials you have, the number of points on that grid just explodes. That's the famous curse of dimensionality. And even worse, it wastes a ton of time meticulously checking settings for dials that might not even matter. Then there's random search. It just picks combinations at random. It sounds chaotic, a little bit silly even, but it's often way more effective. And here is the absolutely crucial insight, which was pointed out by pioneers like Yoshua Bengio and James Bergstra. The reason random search works so well is that usually only a few of the many dials you have actually make a big difference to the final performance. Random search is just much better at stumbling across interesting values for those important dials. Grid search, on the other hand, wastes most of its time by being overly methodical on the dials that don't really do anything. It's a perfect case of working smarter, not harder. So, random search is a great baseline for sure, but can we do even better? Can we actually learn from the places we've already searched to make more intelligent guesses about where to look next? The answer is absolutely yes. This is where we get to a much smarter strategy called Bayesian optimization. So instead of just randomly probing our landscape, this method actually builds a statistical model of it. Think of it like a probabilistic map. It starts with a few random points to get its bearings, builds a very rough initial map, and then it uses that map to decide the single most promising place to probe next. After each new probe, it updates its map, getting more and more accurate over time. It's an elegant loop. So how does it decide where to look next? This is the secret sauce. It uses something called an acquisition function. And this is just a clever mathematical way of balancing two competing goals. The first is exploitation. That means searching near the lowest points we've already found, hoping to find an even deeper spot right next door. The second is exploration. That means searching in completely new regions of the map, areas where we have high uncertainty, because who knows, an even better solution could be hiding way over there. And right there, that is the aha moment of optimization. The truly hard problem isn't just finding a good solution. It's managing this constant trade-off between refining what you already know and exploring what you don't. It's deciding at every step, should I dig deeper right here where I know it's good, or should I go check out that mysterious new hill over on the horizon? Bayesian optimization tackles this trade-off directly, which makes it incredibly efficient. Now, while Bayesian optimization is super smart, we can make the search even faster with methods that are all about getting quick, early feedback. This is where multi-fidelity methods like hyperband come in. The analogy I like is this. Instead of training every single configuration for, say, 100 epochs, which is really slow, hyperband trains a whole bunch of them for just a few epochs. It's like drilling lots of shallow holes everywhere. It very quickly throws out the obvious losers and only invests more training time, more budget, on the most promising candidates. It's all about getting cheap, early signals to avoid wasting resources on bad ideas. So, we've been talking about some pretty cool theory. Landscapes, maps, searching. Let's connect all this back to the real world and see the kind of impact this automated tuning can actually have. Let's go all the way back to where we started, AlphaGo. How much did this fancy tuning actually help? Well, the researchers used Bayesian optimization to tune a key part of the system. And the result? It boosted AlphaGo's win rate against itself from basically a coin flip, 50%, to a dominant 66.5%. Just look at that number. That is staggering. A jump of over 16 percentage points is absolutely massive at that elite level of play. That's the difference between being a strong player and being an undisputed champion. And it was achieved not by changing the core algorithm, but by methodically finding its sweet spot through automated tuning. Now, what if we take this whole idea and just crank it up to 11? Instead of just tuning the dials of a model that a human has already designed, what if the hyperparameters actually define the model's architecture itself? How many layers should it have? What kind of layers? How should they all be connected? This is a field called neural architecture search, or NES, and it's basically like using these powerful optimization techniques to automate the job of an AI architect. And you know what? This isn't just for designing networks. This fundamental challenge of finding the best settings pops up everywhere. Just think about prompt engineering for models like GPT, finding the right sequence of words, the perfect examples to include in your prompt. Well, that's a search problem. You can frame it as a gigantic, discrete hyperparameter optimization task where we're searching for the best input to get the best output. Wow. Okay, we have journeyed through a pretty complex and fascinating landscape here. Let's try to distill all of this down into a practical toolkit for how to think about this problem. I think the most important thing to remember is that there is no single best method. There's no silver bullet. It's all about trade-offs. Random search is your go-to baseline. It's simple, it's surprisingly powerful, and you should never ever underestimate it. Now, if your model evaluations are extremely expensive, taking hours or even days, then Bayesian optimization is the smart, sample-efficient choice. And finally, if you can get quick, early signals on whether a configuration is any good, multi-fidelity methods like hyperband are fantastic for saving a ton of time and resources.
You know, we started this whole journey by revealing that an AI was tuning AlphaGo. Now we have AIs that are designing the very architecture of other AIs. And that leads to a really fascinating, kind of recursive final thought. As we get better and better at automating the design and tuning of these incredibly complex systems, what happens when we turn these tools inward? What happens when the AIs start optimizing and designing the very optimization algorithms that created them in the first place?